Hi, and welcome to YouReallyDoLoveScience.com. My name is Jen, and I'll be your tutor for today. Today we're going to talk about how to write a lab report. Now, I want you to remember that every single teacher is different. And so each teacher's way, your teacher's way, is the right way to do a lab report. For example, some teachers will say, oh, your lab report must be handwritten on notebook paper. Another teacher might say, oh, your lab report has to be on graph paper, of course, because you're going to be doing tables and charts and graphs. And another teacher might say, graph paper? What do you mean graph paper? Of course you have to type your lab report on the computer and print it out. And so each teacher's way is different, and just keep in mind that your teacher's way this year is the right way to do it. There are some things, though, that all teachers seem to agree on when writing a lab report, and so those are the things that I put together here in these instructions. And this particular template is going to be available on my website at YouReallyDoLoveScience.com so that you can print it out and read the instructions later. And let me show you the entire lab report template. It should look like this. This is the one you can print out on my website with all of the instructions. At the top where it says lab report, you want to be able to put the title of your lab report. Determining the relationship, and I'm just making this up, between an object's density and its ability to float. Capitalize that A right there. And I'm just going to make sure that this particular sentence is centered as the title. And there we go. Make sure it's centered. You probably don't want to have the words lab report at the top. Your teacher might like that, but just ask your teacher. So here we have your name, Joe Science Student, with the date and the name of your teacher and period 7 or bell 7 or hour 7, whatever you say. Now, do you remember the scientific method? The scientific method included 5 steps. Step 1 is to make observations. Step 2 is to form a hypothesis about a situation. And number 3, test the hypothesis, like doing an experiment. Number 4 is to record your measurements and your data. And number 5, form a conclusion about the hypothesis. So the scientific method is sort of like the precursor to your lab report. The lab report that you write will be very much like the scientific method in the sense that you state a purpose, then you test it, and you record your data, and then you form a conclusion. So it's very much like the scientific method. And so the purpose of your laboratory experiment, you can use it just 1 or 2 sentences in the purpose. For example, the purpose of this laboratory experiment was to determine whether there is any relationship between an object's density and its ability to float in water. And really that's all you need for the purpose, so we can get rid of my instructions here. And there we go. A purpose can be 1 or 2 sentences just stating why you're doing the experiment. The next part of the lab report is your procedure. So far you've got your title with your name and date at the heading, and then you state your purpose, and now you're getting into your procedure. Now the procedure tells the steps that you did to complete the laboratory experiment. You want to ask your teacher, though, do I need to list every step in the procedure, or should I assume that you know the procedure that we followed and I don't have to get into every detail? I've had teachers say, oh no, you have to write out every step so that somebody reading your lab report, if they wanted to, they could redo your lab in every detail that you did. Another teacher says, no, I was here when you did the lab. I know what you did. You don't have to write out every step for me. So again, make sure you ask your teacher. Ask your teacher also if you should write in the past tense, telling what you did like a story, or if you should write it like a set of instructions that someone else could follow if they did the lab separately from you. Now, there are 2 types of ways to write a paragraph. There's a difference between active voice and passive voice. Active voice sounds like this. We then added 3 drops of phenolphthalein to the solution. It sounds like a normal sentence, right? But then some teachers want you to use passive voice, and you get rid of the pronouns, the personal pronouns like you and we and I, and instead you write it this way. 3 drops of phenolphthalein were then added to the solution. Notice that you can't really tell who did the step in the procedure. It's just that it was done. So when you end up with a procedure, you should normally have a set of steps of what you completed during the lab. And it can be numbered like that. Next is your data section. Now your data, those are your measurements that you make during the lab and your observations as well. This is where your tables and charts go. Sometimes your teacher will have you do 3 or 4 trials of the same exact measurement. This is to ensure accuracy. It's kind of like if you were measuring a plank of wood because you were making something like a cabinet, and before you cut the wood, you made sure you measured it twice or 3 times just to be sure that you measured it correctly. Well, it's the same thing with laboratory experiments. You want to do 3 or 4 trials of the same measurement to make sure you did it correctly and you didn't accidentally make a mistake. So your data tables might have trial 1 and trial 2 with your measurements listed in each row. Now what if you have several trials and let's say 3 of your measurements agree with each other, but then there's this one measurement that's way off and it just doesn't agree with the other measurements and it seems like it's wrong because it's way off. In science we call that an outlier. Usually most scientists delete the outliers, the pieces of data that are way off, because they know that something went wrong. Either they made a mistake or maybe their equipment malfunctioned at that moment. Hopefully you won't have any outliers in your measurements, but if you do have an outlier, a piece of data that's obviously wrong, ask your teacher whether you can delete it. Because if you keep it in your data tables and then it ends up in your calculations in your results section, it can really throw your results off because it's an obviously wrong piece of data. Now I want you to be careful with your units in your data tables. Units are things like grams when you're measuring mass, or milliliters when you're measuring volume, or centimeters when you're measuring length. And you know what units are, but here's how you put them in the data tables. So let's get rid of all of my instructions right here. And let's just create a data table. I'm going to show the ribbon here with all of these features. Look up here at the top where it says Home, Insert, Page Layout. Click on Insert, and underneath the word Insert, there's a table feature. If you click on the word Table, all of a sudden this grid opens up. You get to pick how many rows and how many columns you would like in your table. So let's just pretend right now, we might want to delete some, but let's make it nice and big with 5 rows and 5 columns. Now once it's created, as soon as you let go of the mouse, the data table appears. Let's say you want to adjust the table because you don't like that it's sitting all the way over on the left side of the page. Watch this. You can expand it and make it stretch out. But when you expand it, you've only expanded that one column and it didn't expand everything. So, and let's say we want it to be a little bit, maybe a little bit bigger this way. So if you want it to be proportional and not deformed, what you want to do is select the entire table by clicking on your mouse, select the whole thing, and then go up here to the very top. Over here it says Table Tools, and underneath Table Tools it says Design and Layout. Click on Layout and then go to these buttons right here. These buttons allow you to distribute the columns and distribute the rows evenly. So I've selected the entire table. I want to distribute my columns evenly. Isn't that nice? And now I want to distribute all of my rows evenly. And there I have a nice, even data table. So that's how you create the data table. Again, Insert, Table, and you select the rows and columns. Now we're ready to add data to our tables. I made this up, but let's pretend that we're studying whether certain objects sink or float. I decided we could use a penny. So the first object is a penny, and then we'll say an ice cube. And then the third object is going to be a styrofoam ball. And I only want to measure 3 objects and their ability to float, so I'm going to get rid of this entire row. Now watch, if you type something in a field and then you highlight the row and you just hit the delete button, all it does is delete the text that's in that field. So I'm about to hit the delete button. See how it just got rid of the text? In order to delete an entire row, what you'll do is you'll highlight the row, so you can go up to the Table Tools here, not under Design, but actually under Layout, come right over and see this Delete button. Now click on the Delete button and it says, do I want to delete just one cell or a column or a row or the entire table? I just want to delete the bottom row. So I click on that and then the bottom row is gone. So I'm just teaching you how to adjust your table. So here we have these objects. I guess I don't need a colon there. And then over here, I'm going to say I want to measure the mass of the object, the volume, and its ability to float. And then I'm going to scoot this over a little bit further so that will be big enough. And I'm going to get rid of this column. Now let's say I want the text on these top header rows, this row right here, to be nice and centered. I go back to Home and I click on the Center tab so that these headers are all nicely centered. And now I'm going to fill in some data. Now, we know that mass is measured in grams. We have several choices in some data tables, and as a matter of fact, I'm going to make all of this data centered as well. So let's say the penny's mass is 2.49 grams. You have a choice of putting grams right there in each cell with the number. But what's commonly done with data tables, instead of entering the G for grams each time, what you want to do after the word mass, you do parentheses and then you list the unit. So that says mass in grams. The parentheses means it's in grams. Okay, so I've got the penny's mass is 2.49 grams. At volume, we're going to measure volume. For solids, it's going to be in cubic centimeters, and for liquids, it's going to be in milliliters. But all of these objects are solids, so we are going to measure the volume of these objects in cubic centimeters. Now, the 3 needs to be a superscript up high. So we go up here and we click on x squared, and that gives us the superscript feature. Then you click on it again to come back to regular font. The ability to float is just going to be a yes or no. And let's pretend that we did this lab and no, the penny couldn't float, and oh yes, the ice cube was floating nicely, and the styrofoam ball, yes, it floated nicely. Now let's fill in these volume measurements. And for the penny, and there's no way that you would know this, I'm just making up these numbers as if you had measured these things. For the penny, we're going to say 0.349 cubic centimeters. For the ice cube, 12 cubic centimeters. And for the styrofoam ball, we actually measured the diameter of the styrofoam ball. We cut that in half to get the radius, and then we did the equation for the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. The diameter was 4 centimeters. The radius was therefore 2 centimeters. And in the calculator, when I calculated 4/3 times pi times the radius, which is 2 centimeters cubed, I end up with a volume of 33.51 cubic centimeters. And so this is an example of a data table. It's complete. Every field or every cell is filled in. Sometimes these cells, these little blank areas, are called fields in other programs. So cells and fields are basically the same thing. And so we have a nice complete data table here. And most data will be in the form of a table, but there's some data that you could record in the form of a paragraph or some other form of chart that you could, where you could put your measurements or your observations, for example. Now we move on to the results section. The results section is where you show your calculations. You're going to talk about what you figured out with your data. What did the data tell you? Now we have an example here about density and floating. So we're going to calculate all of the different objects' densities, and we might make a new table showing the densities, and we'll compare those densities to the object's ability to float. The density formula you should know, it's density equals mass over volume. You're going to ask your teacher, hey, do I have to show my calculations? And what I mean by that is density equals mass divided by volume. And then you're going to plug in numbers. So let's say for the penny, we say density equals, and we've got a mass of 2.49 grams. And a volume of the penny was 0.349 cubic centimeters. So you're going to show your work this way, You might be able to do it by hand on regular notebook paper. And then once you do the calculation, the density of the penny turned out to be 7.13 grams per cubic centimeter. And that was using a calculator. So do you see how we showed our calculation? Ask your teacher if you have to show your work for every single calculation in the lab, or are you allowed to show it once to prove to her that you know how to do the calculation, and then for the rest of the calculations you just do it on your calculator or on scratch paper, but you don't have to show it in the lab report. So that's different for every teacher. Once you have a calculation, at least one, shown, then what you want to do is create a results table. Sometimes there's a results table, sometimes there's not. There's some results that are just paragraph form. But in this lab, we are going to, and let me take this data table and see if I can copy the whole thing. I'm going to right click, see if I can copy this entire table down here. See if it works. It did work. So now we will, instead of showing the mass and the volume, because those were measurements that we made, I'm now going to say the density of the object. And the density of the object would be in grams per cubic centimeter again. Okay, so once we calculated the penny's density, it turned out to be 7.13. And we, again, you don't put the units in the field, just at the top in the header. And for the ice cube, we took mass divided by volume. And for the ice cube, the density is 0.9167, 0.9167. And for the styrofoam ball, the density turned out to be 0.300 grams per cubic centimeter. And so do you see how after you do calculations, those are your results? And so we created a results table. Now this section in your results section is also a place where you're going to explain your sources of error, the things that didn't go perfectly. Now in every lab there are going to be mistakes or measurements that weren't exactly right. Sometimes you have equipment that's old. For example, maybe you used a balance that's very old and it was wobbly and it never really could get evenly balanced. Or perhaps the thermometer was old and you could see the red fluid, which is alcohol, in the thermometer, but you could also see a little air bubble in there, so the thermometer was not reading accurately. Or maybe there's human error. Maybe you made a mistake when you were reading the graduations, which are the markings on the thermometer or on the beaker or on the flask. Or maybe you spilled some of the substance just slightly, or maybe when you transferred the substance from the filter paper into the volumetric flask, not all of it actually made it into the flask just because some of it stuck to the paper. There's all kinds of reasons why your results are not perfectly accurate. And so in the results section, you want to explain first by calculations whether your results were accurate, and then you want to explain in words about whether your results were accurate and why, the reasons why. Now, after you create your results table and report the numerical results, you then want to be able to talk about whether your results were good or not. And there are two ways to evaluate your results. First, you have accuracy. And accuracy is whether you got the right answer. Accuracy is how close you were, how close your results were to the accepted value. And when I say accepted value, I mean there was a right answer, or there was a density, for example, for styrofoam that you could look up in a book, and it was an accepted value for the density of styrofoam that you knew to be the true density of styrofoam. And so you're wondering, well, how close did we get to that accepted value? And accuracy is measured by percent error. Now, percent error is basically the difference between your result and the accurate result, or the accepted value. And the equation for calculating percent error goes like this. You take the absolute value of the difference between your result and the correct result, or the accepted value. You find that difference, you divide it by the accepted value, and then you multiply by 100. I took the absolute value on top because I don't want my percent in the end to turn out to be a negative percent. So let me give you an example here. Let's say that the correct density according to a textbook of a certain metal is 9 grams per cubic centimeter. But in your lab, you took measurements, and in your results section, you did density equals mass over volume, and you calculated the density to be 9.27 grams per cubic centimeter. So you were off by 0.27 grams per cubic centimeter. So here's how you calculate your percent error. You take the difference between your results and the accepted value. It doesn't matter which one comes first, you're just finding the difference between the two. So 9.00 minus 9.27, which is 0.27. Or, if you want, you could say 9.27, which was your result, minus 9.00, which is the accepted value, which is a negative answer. But because you're taking the absolute value of that difference, it doesn't matter that you ended up with a negative value on top. So you take the difference between the right answer and your answer, divide it by the right answer, the 9.00 was the accepted value, and multiply that whole thing by 100 to get your percent error. See how easy that is? This is a way of measuring how accurate your results were. And if you have anything under 10% error, then it means you really did a good job in your lab. Sometimes I don't include all the units in my calculations, but some teachers want you to include units next to every single number, so make sure you do what your teacher asks you to do. Now you could end up with a lab where your percent error is something crazy like 80%. That would mean that either you did the calculations wrong, or your equipment malfunctioned, or maybe something spilled and you were not able to get a good result. In college, if your percent error is high, you actually could fail the lab and get a very bad grade. But in high school, usually the teacher will accept an explanation as to why the results turned out bad or were inaccurate. In other words, if you understand the calculations that you did, the measurements that you made, and the purpose of those measurements and calculations, and if you can explain the purpose and why the results were off base or your percent error was high, your teacher will usually accept that as good enough because she knows you understood the concepts. So ask your teacher if a high percent error is going to ruin your grade, or if you can just explain your sources of error. Now, so when your error is high, make sure you spend extra time explaining what could have gone wrong in your experiment. Once again, it's percent error that measures how accurate you were. In other words, how close you were to the correct value or the correct answer. But then there's something else about your results that your teacher might want you to explain. The second way to evaluate your results is called precision. And precision is about consistency. So precision answers the question, how consistent were your measurements or your results? Now remember that you could be consistent and you could still get the wrong answer. For example, if you have a bathroom scale and every time you step on the scale, it's 5 pounds off, but it's consistently 5 pounds off. Well, that's a scale that's not accurate, but it is consistent. And so precision and accuracy are very different. And when you say your results were precise, you're saying that you were consistent. It's best to have both good accuracy and good precision. Consistency is important because it usually means that you were being careful when you did the lab and you weren't doing different procedures. You were actually doing the same procedure each time very carefully. Precision is measured by percent deviation, and percent deviation has a different equation. So with percent deviation, you really are telling how close or how far your measurements were from each other. In other words, how consistent you were. So here's how you calculate whether your measurements were consistent. If you didn't have any big outliers, if most of your measurements and your calculations were pretty close to each other, then your percent deviations will be low, which means good consistency, good precision. If you had one measurement that was way off, then your percent deviation for that trial might be higher, And a high percent deviation means that something else went wrong. That result or that calculation or that measurement deviated from the others. And for that trial, you might have a higher percent deviation. If your results are consistent, it means you were careful. And that's why percent deviation matters. The way to calculate consistency is called percent deviation. First, you get the average of all your results. Let's say we did 4 trials in the lab, and we did 4 sets of calculations, and we ended up with 4 different sets of density values. And I just made up these numbers here. In order to get the average, all we do is we add them all up, divide by 4, and there we go. There's an average. And again, this is for some kind of a liquid. I just made this up. So I used a calculator and I got the average. Percent deviation talks about how far off was each measurement from the average of all your measurements, or the average of all your results. So you'll take the result from one trial and you'll subtract it from the average of all your results, get the absolute value of that, divide it by the average, and multiply by 100. So let's do this for the example. Trial 1, looking back up here, the density of trial 1, the density of the fluid turned out to be 0.906 grams per milliliter. Let's plug that in down here. Subtract the average result, which we found to be 0.931 grams per milliliter. Take the absolute value of that, which is 0.025. Divide that by the average, 0.931, and multiply by 100. That gives us 2.69% deviation for that trial. I used absolute value on top again so that I wouldn't get a negative percent in my answer. You'll have to do percent deviation for each trial if your teacher does want you to do percent deviation to show your consistency. At the very end, your teacher might want you to write a few sentences about your results, not just show the calculations. And so you've got your percent error and your percent deviation numbers, but then you want to add a few sentences about the quality of your accuracy, which was measured by percent error, and your precision, which was measured by your percent deviation. You can say something like, our data was fairly consistent, with deviations ranging only from 2% to 6%. And so that's your results section. You'll end up with a results table, something like this one up here that we did. You'll show calculations, either above the table or below the table. You'll do your percent error calculations. Then you'll do your percent deviation calculations. And then you'll add a paragraph or a few sentences discussing your results, whether your results were good or not. And finally, your sources of error. And so your results section is really the biggest part of your lab report because it includes your calculations, your results tables, charts, or graphs, and you should ask your teacher if she wants you to graph your results. Your calculations regarding your accuracy, which is your percent error. Your calculations regarding precision, which is based on percent deviation. A few sentences discussing whether your results were good or bad. And your sources of error. The sources of error are what we've talked about already, what might have gone wrong or what might have thrown off your results. Your conclusion is kind of fun and short and easy because all you have to do is just answer the question that you stated in the purpose. Was there a relationship between an object's density and its ability to float? Tell what you discovered. So you could say something like this. Based on our observations, our data and calculations, we found a clear relationship between an object's density and its ability to float in water. Specifically, we discovered that objects with densities higher than that of water sink, and objects with densities lower than the density of water are able to float in water. Remember, if your teacher wants you to use passive voice, then you'd say something like this. Based on the data and calculations that were made, a clear relationship between an object's density and its ability to float was observed. Notice that you're not saying who did it. You're not saying I did it or we did it. You're just saying that the relationship was observed. So now you know how to do a lab report. And I just have a few reminders for you. Lab reports are not hard to do, but they take so much longer than you ever think they're going to take. It's not something you can do at your lunchtime or between classes. They're like school projects. You really need to set aside at least one evening to do a lab report properly, especially the results section takes time. I want you to be careful. I want you to do your calculations twice and check all your work, and please be very, very neat. Make sure you do everything your teacher's way. If your teacher disagrees with me on something, then forget about what I said and do it her way or do it his way. And above all, I want you to be safe in your lab. Follow the procedure carefully. Don't fool around too much. You can have fun, but don't do anything stupid that could get somebody hurt. And so be safe. Wear your goggles, even though they're silly looking. And I hope you get an A on your lab report.